In our last session, we're going to conclude talking about association rules. Let's see where we left in the previous session. First of all, we established that association rules are used for finding out what goes with what in terms of items that come together in a basket. But of course, a basket doesn't have to be a physical basket or even a virtual shopping basket. It can be a combination of items such as symptoms in a medical database. What association rules do is they generate if-then rules that help us find dependencies between different items that tend to come together. We talked about generating lists of if-then rules using the famous a priori algorithm. And the idea there is to create these frequent item sets where we start with single popular items and then expand them into pairs of items and triplets and so on. We also talked about the notion of support for determining what is frequent or popular. And after we set that threshold, only then can we actually go and generate rules in a way that doesn't explode in computational time. Now the question is, once we've generated these rules, how do we pick the ones that are actually true, that are indicating relationships that are not random? We're going to talk about two particular measures that will help us pull out the useful rules. The first measure is called confidence. And if support was simply the proportion of items in the whole database, whether it's a single item or a pair of items or a set of items, in confidence we're looking at a conditional probability. Here we are distinguishing between the antecedent and the precedent. The confidence is defined as the percent of antecedent transactions that also have the consequent item set. And what this means, if we want to compute this percentage or probability, we're going to look in the numerator at the number of transactions that have both the antecedent and consequent item sets, so the if and then, and divide that by the total number of transactions that have the antecedent in them. And of course, that will likely be a larger set. Let's look at an example. Suppose that we're trying to detect an influenza outbreak, and we know that people who have the flu or flu-like symptoms tend to buy orange juice for the vitamin C and tend to buy Strepsils and perhaps also tend to buy soup. So let's look at a large supermarket database and suppose it has 100,000 transactions, and each transaction is a basket of a particular customer. Across these 100,000 baskets, we find 2,000 baskets that contain these two items, orange juice and Strepsils. And among these 2,000, 800 also include a soup. Let's see what we can say about the confidence of these rules. So first, let's look at the support. What is the support of a rule that says, if orange juice and Strepsils are purchased together, then soup is also purchased on the same trip? Stop the video for a minute and see if you remember how to compute the support for this rule. If you remember, the support doesn't really care what's in the if and what's in the then. It's going to look at both the antecedent and the consequent together. And if we look at the baskets that have all three of these items, orange juice and Strepsils and soup, we see that we have 800, and we divide that by the total number of baskets that we have, which is 100,000. That gives us a support of 0.008, or in percentages, 0.8%. Now let's look at the confidence of this particular rule. So we want to ask ourselves, what is the confidence of this rule? If orange juice and Strepsils are purchased, then soup is purchased on the same trip. Stop the video and see if you can compute this on your own. When we're looking at confidence, we're looking at a conditional probability. So given that you see orange juice and Strepsils, what is the probability that you also purchase soup? What are we going to do here? We're going to look at the number of transactions that have all three, which is 800 transactions, and divide it by the probability of orange juice and Strepsils, which are 2,000 of these records. And what we get is a probability of 0.4. In other words, the confidence of this rule is 40%. What is the problem with using confidence? Well, here's the problem. If some of the items in the antecedent and or the consequent are very, very popular, such as bananas when you're shopping in the United States, then you're automatically going to get high confidence. But that's not necessarily going to indicate that this is an interesting rule. For that reason, there's another performance metric called the lift ratio, not to be confused with lift, which we talked about in the context of classifiers. The lift ratio looks at the confidence after dividing it by some kind of a benchmark confidence. And in particular, what this benchmark is it says, let's assume that these items are completely independent. And we'll try and see how much better we're doing with our rule relative to the case where these items are completely independent. So independence between the antecedent and the consequent means that the probability of both of these events happening is equal to the multiplication of the individual probabilities. Probability of A and B is equal to the probability of A times probability of B. That is a definition of independent events. So what we have is that the benchmark confidence is going to be the probability of the consequent given the antecedent. But if these two events are independent, I can drop the condition here and say that this is equal to simply the probability of the consequent. The probability of the consequent, or the support of the consequent, is simply the percentage of transactions with these consequent item sets. In other words, I'm counting the number of transactions with the consequent item sets and dividing it by the total number of transactions in the database. So we're calibrating our confidence by dividing it by this benchmark of independence. And what this means is that the lift ratio should be larger than 1. If the lift ratio is larger than 1, this indicates that this rule is more useful than just some kind of a random choice. If the lift is equal to 1, it means that our rule is no better than random, that the numerator is equal to the denominator, which is based on independent events. Let's see if you can compute the lift ratio for the same rule that we looked at before. If orange juice and Strepsils are purchased, then soup is purchased on the same trip. Think about whether the information that we had thus far is sufficient for computing the lift ratio. And if not, see which one of these other 4 pieces of information is needed in order to do the computation. Stop the video here and see if you can figure this out. So we've talked about generating the rules, and now we have to choose the rules that are going to be non-random. The idea in association rules is to generate all the rules using the a priori algorithm and the support threshold, and then use confidence to also threshold the rules that we want. This is going to help us find frequent item sets, the ones that have sufficient support, and then among these, we're going to only look at the rules that have sufficient confidence. So we're also going to have a threshold on confidence. Once that happens, we're going to look at the lift ratios and choose the rules that have high lift. Let's go back to our cell phone faceplate example that we introduced in the previous session. And the example there was of a store that sells accessories for mobile phones that runs a promotion on faceplates. And in particular, they have 6 different colors, and they want to find out which combinations of colors customers are likely to purchase together. Our data looked like this. We had 10 transactions for the first day. And what we did in this view is transform the data into a data matrix form that is similar to the data matrices that we've seen before. So we have transactions in rows, and we have colors in columns, and we use binary zeros and ones in order to determine whether this particular color was purchased in this particular transaction. So in transaction number 1, we see that colors red, white, and green were purchased, while the others were not purchased. The first thing is to compute the support for each one of these item sets. We start with single items. So for instance, the item set red has a support of 6. How do I find this number? Well, if I look at each and every one of the 10 transactions, I'll find that 6 transactions contained a red faceplate. And I can keep expanding this whole set of item sets and count the support for each of them. Let's look at this example where I'm looking only at 3 colors, red, white, and green, and ask myself, what is going to be the confidence of red, if red and white, then green? And if you do the calculations, you'll find that this gives us a confidence of 50%, because the support for red, white, and green is 2, and the support for red and white is 4. Similarly, I can compute the confidence for if red and green, then white, and find that it has a confidence of 100%. There are going to be 4 more rules for these particular 3 colors, and if you do the computation, you'll find that they have confidence of 100%, 33%, 29%, and 100%. So if I set a threshold of 70% confidence, how many of these rules would qualify? Well, the 100% would qualify, 1, 2, and 3, while the others would not qualify. Let's look again at what lift ratio means. So remember that a lift ratio, which compares the confidence to a benchmark confidence, shows how effective the rule is in finding consequence versus just a random set. This is going to be especially useful if you're looking for particular consequences that are interesting to you. If we look at confidence, this shows us the rate at which the consequence will be found. And this is going to be useful if I'm trying to learn the costs of promotion, for instance. And finally, the support measures the overall impact because it looks at the percentage of transactions that are affected by these rules. Now, there's still going to be a problem of finding random rules that are just there by chance. And the reason is we're working with lots and lots of rules, and we're likely to have some of them that will still pass through our filters but are indicating some randomness. When is this going to happen? Well, the more rules you produce, the more risky it's going to be. So you want to try and reduce the number of rules that you're trying to produce, not only by setting the thresholds high, but by also a priori saying, I only care about these particular items or about these particular combinations from an operational point of view. The other issue is that you want to use as many records or transactions as you can, because rules that are based on larger numbers of transactions are less likely to be a result of chance. So to summarize, association rules, also called affinity analysis, market basket analysis, produce rules on association between items or columns. And in particular, we're looking at databases of transactions or events of interest. This is not the same as recommender systems that use collaborative filtering. And the most popular method for generating the rules is the a priori algorithm. This helps us find a fast computational way of generating rules from a large transactional database. In order to reduce computational issues, the trick is to consider only these frequent item sets. And these we get by deciding on some kind of a threshold on support. In other words, we're trying to only look at the popular items. After generating this large list of rules, we try to filter them out by first setting a threshold on the confidence and secondly looking at rules that have high lift ratio. Still, we might encounter rules that are there by pure random chance, and therefore we want to make sure that we also take into account our domain knowledge and operational constraints. We also want to remove redundancy by compressing and condensing rules that are very similar or identical. So with this, we close association rules, which was our last unsupervised learning technique. Hopefully you've enjoyed these videos. We send you again to go and read the book and then move on to the online forum.